Hello everybody. You're watching a Novartis Enterprise Architecture training session. We hope very much that you will enjoy the information we share, and we welcome any feedback you want to share with the architecture community. In this session, I will introduce the concept of patterns and use a couple of real-world analogies in order to illustrate this concept's real power. Also, I will introduce the concept as well as utilization of a pattern language, where roughly spoken such pattern language is a system of patterns. Further, I will demonstrate how patterns are very practically used within an IT context and how they are turned into executable code very efficiently. In fact, I will very quickly implement one of SAP's key features based on an appropriate software design pattern. Further sessions later on will explain how patterns are utilized and applied for the benefits of Novartis. So as just mentioned, and before we dive into the topic of IT architecture related patterns, we want to introduce the pattern concept more generally first. Let's start with the simplest of all questions. What is a pattern anyway, and what ingredients does a pattern decompose into? Well, the answer is quite straightforward. A pattern is comprised of a description of context, which may determine a context-specific value system, scope, or inherent intent. Then the expression of a problem, which we could also call a system of forces, which can be observed to occur over and over again. And last but not least, the description of a solution, which is proven to adequately respond back and solve the respective problem. That's already it. Now, I admit that even though I have outlined all three ingredients here, there are many questions that remain still open. For example, the question, what form does a pattern take? So, what form does a pattern take? There is no one single answer back to this question. A pattern can already exist and be used by silent and common agreement, so for example as an established term in our language. Let's look at an example. Think of the terms bike and train as they are sketched here. We could call the context within which both terms occur mobility. Also, both terms refer to an inherent problem that they claim to tackle. In the case of the term bike, this problem can be described as I need to get from A to B, where A is not more than max 20 kilometers apart from B. I don't require heavy weather protection, I'm not in a hurry. Also, I want to exercise a little bit. In the case of the term train, the attacked problem could be described as I need to get from A to B, where A is more than 20 kilometers apart from B. I want to be weather protected, and also I want to arrive in B quickly. Finally, I want to work on my computer during my travel. So you see that there is no formalism required, quite the contrary. We seem to use patterns already intensely as well as efficiently and on a daily basis out there in real life, and in order to orientate ourselves regarding the most adequate solution for the problem at hand. Having said that, these patterns still seem to be a little vague and fluffy. Ultimately, they seem to not really match what we see as ideal problem-solving techniques usually. Problem-solving techniques we ideally expect to tell us exactly what to do when. We love them to be almost procedural advices and overly tangible assets like SOPs, standard operating procedures, work instructions, project plans, and that like, right? Well, and patterns so far do not seem to be of exactly that nature, but let's see. So how concrete is a pattern indeed? Well, a pattern is very concrete on the level where it describes all aspects and forces which span context, problem, and solution. Think of the bike to example I had just introduced. We said that the context is clear and we termed it mobility. Then we said that the problem statement could be I need to get from A to B, where A is not more than max 20 kilometers apart from B. I don't require heavy weather protection and I'm not in a hurry and want to exercise a little bit. Now think a second about it. There is a ton of further insights which come with this pattern. There are consequences and implications we are immediately aware of when we hear the bike tour term somewhere. For example, that we will get wet when hit by a storm. Also, and depending on the actual route we are traveling, for example when it goes uphill, chances for us to sweat and require a shower when we arrive in B are huge. This in turn tells us we are well advised to put a fresh shirt into the backpack. Also, we should take some water with us, right? Well, there is a lot more that we immediately associate when we hear the term bike or bike tour, and these associations are quite useful and tangible. So I would say that this part of a pattern is quite concrete indeed. However, and while being concrete, patterns are also quite generic. The bike tour pattern applies to each and every other bike tour that we ever planned in the past, are in the process of planning right now, as well as those bike tours that we once planned somewhere in far future. So let's remember this. A pattern is what its name says. Its very nature is generalization. A pattern refers to an idea, concept, phenomenon that we can describe and name concretely, like bike and train, while at the same time it generalizes all concrete bike and train tours that ever occurred, as well as those that will ever occur in future. Having said that, a pattern provides us with tons of useful advices of what we should better do, not do, what we need to be aware of, for example rain on our way, etc. This means that patterns are a very useful and concrete utility also that help us to take informed and good decisions over bad. This combination of being generic, reusable and broadly applicable while providing very concrete advices on the other hand side makes patterns a very powerful technique for all architects as well as for non-architects out there. Now let us leave bikes and trains behind and look at another more architecture-ish example. Along the pattern's ingredients we define the context to be urban architecture this time. The problem which we can observe there to occur over and over again if we have a building with more than one floor is the need to change between floors. Let's look at the sketch quickly. Now, how does an appropriate solution look like? You can see it already. Well, the solution which this pattern suggests is to take the height between floors, chop it up into equally sized bricks that one could easily step up, then arrange the bricks as outlined here in this sketch and make sure that there is a hole in the next floor above. Clear. You know this pattern perfectly well, similar to the bike pattern example beforehand. We call this pattern stairs. Also, we recognize there is quite some information further associated with the term stairs that we now have immediately available to us. For example, if stairs is indeed the solution we choose to address the recurring problem of having to change between floors in a building, then this means we need to actually move ourselves up those stairs. This requires some level of fitness. Also, if heavy bags are to be carried upstairs, the stairs pattern might not be the most adequate one anymore. Furthermore, we could stumble, fall down the stairs and be painfully hurt. All these insights and thoughts we have immediately at our fingertips, so we can actually start to quite consciously reflect on the adequacy of stairs in order to solve the problem that we are confronted with here. While we saw that patterns are very useful and provide us with orientation and a load of useful associated insights, a question remains. Does this mean that a pattern solves all my problems? Good catch. The answer to the question is obvious and simple. No. Not even patterns solve every problem on this planet Earth. To be more precise, patterns neither replace your thinking and final decision making, nor do they establish concrete stairs for you magically. Building the stairs is something that remains to be manually done by you. Let's quickly follow the sketches here in order to see how differently stairs can actually be built out. I will mark the different realizations of the pattern, of the stairs pattern, in red here. So let's quickly wait for them to be done. So while the stairs pattern provides you with concrete conceptual means and guidance to very consciously reflect on its realization's pros and cons, the last mile remains yours. And still there, you have a broad variety of flavors available to you when it really comes to get your hands dirty and stand up your specific stairs. So these final choices remain yours, And while they are the real work to be finally done, the pattern and its utilization made sure that the decision you took is meeting your needs adequately. While finally the patterns make sure you are doing the right thing over the wrong, while still you or your craftsman has to make sure the right thing is done right by physically building it right. This slide shows two more examples of how differently the stairs pattern was implemented here. Both photos I took in beautiful Ticino, Switzerland's southmost canton. The material used here was granite. Now we have understood that patterns are concepts and ideas that span a potentially infinite and very broad variety of respective realizations of them. Realizations like the stairs here in the Ticino canton. Well, now that we have done that, the big question remains: how would I actually find useful patterns, and what if there are more patterns than just a single one for a problem that I had to solve? Okay, the question is fair. Usually there are more patterns, i.e. alternative solutions for one and the same challenge at hand. Just think of the stairs pattern quickly. Two related, here, similar patterns which are sketched on this slide are rope ladder, where you need your arms and legs, which makes it a little different from stairs, and elevator, where you do not move yourself, but where the stairs move for you, so to speak. However, equivalent or similar patterns, thus patterns solving the same problem, are not the only pattern relations that we should think of. There are also complementary patterns to stairs. A whole set of related patterns is called a pattern language, and we will see in a second what a pattern language is in more detail. The term language is well deserved, since such network or system of patterns can be traversed, utilized, and applied to a broad variety of complex problems in an overly flexible manner. Very similar to how we can flexibly form an infinite number of correct statements over a human language. But let us first look at this from a broader perspective. Most of our today's real-world problems are nonlinear and complex by their very nature, i.e., heavily interwoven and interdependent. Therefore, they can oftentimes not adequately be attacked by linear and procedural logic. This traditional approach is illustrated here on the slide. Assumption is that the activities, decision points, etc. outlined in the problem-solving algorithm are sufficiently smart to cope with the real-world complexity, while at the same time their orderly arrangement can be fixed once and forever. This may be an okay assumption for simple problems, but is designed to fail if complexity grows. A pattern language, instead, takes a different approach by outlining atomic, somewhat agnostic, reusable and relevant nuggets of insight, where the individual pattern's relationships are made explicit at top. This network of insightful nuggets, as I call them here, is formed based on a broad variety of relationship types. To name just a few, you'll typically find relations like similar to, equivalent to, complementary to, specialization of, part of, etc. The beauty of a pattern-based solution approach is that the algorithm to solve a complex problem can now be created ad hoc by strolling through the pattern network and by spotting those patterns that help the problem's solution in the most adequate fashion. In other words, a pattern-based solution approach is overly adaptive and doesn't encode heavyweight assumptions already into it, which in contrast, the problem-solving algorithm approach does quite a bit. To summarize, problem-solving which favors a fixed procedure that leaves individual steps open to the moment in time they get executed is turned upside down by the pattern approach. The pattern-based solution approach favors a network of solution spots, nuggets of insights, or simply just patterns, and trusts the problem solver to pull the right set of patterns as well as to arrange them to solve the problem at hand. Now let's have a look whether this network of patterns concept exists all around our stairs pattern as well. If we think a little about it, then stairs-related concepts indeed come to mind. For example, entresols, as sketched to the left, which often connect stairs and open up space for small niches, cozy places, etc. Or, as another related concept, roofing, which stairs may require if they are fully or partially outside of buildings. This is roughly sketched here in the middle on the slide, as you can just see. Well, there is another concept, balustrades. Clearly, the balustrade pattern would go beyond stairs, but also stairs require crash barriers to protect people from falling off when they stumble. That's sketched right here on this slide. So indeed, we were able to immediately spot further concepts and patterns which were clearly related to our stairs pattern. So we can say that a pattern language is a tool which systematically raises an architect's awareness for complementary patterns. By doing so, a pattern language ensures the completeness, correctness, and relevance of developed solutions and makes the solution development a conscious and not accidental process altogether. This slide summarizes what we had just said. Also, it shows an excerpt of a pattern language that spans beyond stairs. If we were to solve the problem of changing between floors in a very concrete situation, and we had this language available to us, then we could very consciously stroll through it, pick up those patterns that we deem adequate during our decision-making process, and leave those aside which we don't. Thus, finally, we may come out of this process with the following more holistic solution. We will use stairs to connect floors over elevators or rope ladders, since stairs better balance costs and convenience. Furthermore, we plan extra roofing in front of the house and where stairs will be unprotected from weather conditions otherwise. Entressols will be introduced to allow people to move between floors more conveniently and potentially have a rest if they need to. Last but not least, balustrades will make sure that our stairs can be used safely, where finally we will have balustrade gate at all start and all end points, which protects small kids from entering the staircase mistakenly, ultimately from preventing small kids to fall down the stairs. So by now we hope that you have seen how powerful patterns are in our day-to-day life. Next we will demonstrate the power of patterns when used in IT. In order to illustrate the use of patterns in a real IT context, I have decided to walk through an example rather than to just generally introduce patterns again, more or less. So let us say that for now the context ingredient of a pattern is set to IT. Next, let us look at the problem statement. In order to get there and have something to chew upon, which is fun, let us ask ourselves the following question. If SAP was not there yet, and we were to invent its fundamental idea of deferred customization, then how would we actually achieve this? Okay, right. First we had to distinguish between two major aspects. That there is the aspect of a generic and foundational framework on one hand side, which is those proportions of an SAP system that would never change, and that there is another aspect of customizable components, thus components that can be tailored to whatever specific needs a company, which is adopting the foundational framework component, actually has. The specific relationship between the before mentioned aspects is that the foundational framework pre-implements, let's say, 80% of any SAP installation, and that on this level, customization hooks are foreseen for any further implementation-specific adjustments. The other aspect is that whenever that framework gets purchased and implemented within the context of an appropriate enterprise, then the actual adjustments and customizations, so the remaining 20%, still need to be done. So again, the generic framework underpins any of its implementations. For example, this means that it has its generic proportions of an end-to-end process already pre-implemented and hardwired in its compile base. To be a little more precise, let's pick SAP's HR module and one of its core backbone processes like the employee lifecycle process. Let's further assume that this process is going down all the way from hiring a person to laying off that same person again somewhere in future. To be more concrete, let us assume that SAP's research department detected that the fundamental flow of events throughout an employee's lifecycle in all companies is to hire the person, to use that person, and to then fire and finally forget that person. So while there is generic logic on the process level, concrete implementations of all individual process steps are always deferred to an appropriate implementation project. If we said that two companies, A and B, purchased the same SAP HR module as a commercial off-the-shelf package, then both companies would have bought the exact same backbone process, where this process is part of the SAP core systems compile base. We could also say that the employee lifecycle process algorithmic structure could not be altered by neither A nor B. The good thing, however, is that SAP made their HR module customizable. Therefore, both A and B could possibly have significantly different implementations of their HR systems by differently implementing the individual process steps respectively. So to summarize, when the algorithmic process structure of the employee lifecycle process is final and fixed, each of this algorithm's individual steps is up and open for tailoring and appropriate customization by any enterprise buying the SAP HR system off the shelf. So far, so good. Now let us assume that we wanted to build such a core SAP HR system, and let us further assume we wanted to use architecture patterns as much as possible to not reinvent design wheels again and again. First question should be, how shall we express our problem? Well, first we need to be able to implement the final process logic, i.e. the algorithmic structure, and make sure no one is able to fiddle with this anymore later on. This needs to happen on the level of our SAP core system, i.e. the foundational framework, as we called it beforehand. So this part would be an SAP company's process contribution. On the other hand side, we also want to be able to defer the implementation of all individual process steps to a later stage. This is important because SAP does not know how company A prefers to hire a person, in contrast to how B wants to implement their hiring step. Okay, now what I have brought up here is a software design pattern catalog from the internet. Let's go and scroll through in order to see whether we find a pattern that matches our specific need. I give you a second before I lift the secret, in case you want to do the problem to pattern matching yourself. Okay, here we are. This pattern here sounds quite promising. Define the skeleton of an algorithm in an operation, deferring some steps to subclasses. Template method lets subclasses redefine certain steps of an algorithm without changing the algorithm's structure. Honestly, to me this sounds quite perfectly fitting. So we have found a pattern candidate. Next, we have to give this candidate a closer look in order to see whether it can really carry our deferred customization load. But I'm quite confident. So let's give the template method pattern a closer look. The description that you can see here on the slide I have brought to the deck from the internet. In the template method of the template method design pattern, one or more algorithm steps can be overridden by subclasses to allow differing behaviors while ensuring that the overarching algorithm is still followed. So when we turn this to object-oriented programming, then a class is created that provides the basic steps of an algorithm design. Here this class is called base class. And then furthermore, stubs for those basic steps are created based on abstract methods. When later on subclasses are created, then the subclasses of base class can override, i.e. modify, the abstract methods of base class in order to implement their subclass specific behavior. So this shows nicely that the generic algorithm is kept final on the level of base class, where its concrete steps will only be implemented if subclasses inherit from base class, as well as when these subclasses override the abstract methods of base class accordingly. In the general template method pattern description here, we have two subclasses, child class A and B, overriding the hook methods, hook method 1 and hook method 2, of their superclass base class. Well, I would say that this is exactly what we were watching out for. Now the final step that we still need to tackle is to apply the template method pattern to our concrete problem. You remember the two stairs in front of the Ticino houses? Very similar to how the stairs pattern had to be applied and used as an input to standing up those granite stairs for the Ticino houses, the template method pattern has to be applied now to our SAP HR module. I've already done this here for you. Please first note that I've flipped the generic framework to the top and the customized components moved to the bottom of the slide. What is more interesting though is the UML model to the right. There you see a class which I called SAP HR, which corresponds to base class in the template method pattern on the previous slide. For methods in this class are kept abstract, which means that the framework developer explicitly defers implementation of these methods to respective child classes once SAP HR gets adopted within a concrete enterprise's context. In the example here, we show two different implementations of SAP HR, one for Enterprise A and another one for Enterprise B. The two are called SAP HR A and SAP HR B. The method lifecycle manage in class SAP HR obviously corresponds to the method that was called template method in template method design pattern description on the previous slide. Furthermore, we see how SAP has decided to generically implement this method based on their experience and respective research. So if a person gets hired, that person will be used by the company, then fired, and finally be forgotten about. So what we have here is a very concise blueprint of a design that we can and will implement now in Java. However, and before we go there, the key point you should note here is that the template method pattern has given us a jump start to pick the right decision and the right design for our problem at hand, and has conceptually outlined an ideal and proven design that we only had to finally apply to our concrete SAP HR system and our problem to solve. The pattern already told us about the consequences of applying it, its static as well as its dynamic structure, the key components that its design is based upon, as well as these components' responsibilities. All this we could just reuse without squeezing our head an inch. Now the last bit is ours, obviously, and you'll see me now put on a Craftsman blue color suite and implement the whole thing in Java. Alright, so I have already set up myself over here. I have brought up Eclipse here in the background and also created stubs for the respective classes, as you can see, person, SAP HR and so forth. So I've created the respective skeleton classes already, which correspond to the UML diagram over here. I will start off with the implementation of the first class, person, because this is rather a supplementary class. Nevertheless, we refer to it quite a bit, so it makes sense to get started over there. I want to give a person two properties or two attributes, one being name, which I initialize with null over here, and first name is the second one. I also set it to null right at the beginning. Now we need a constructor, which I create over here, and I want to be able to initialize both attributes in one go. So I create a constructor with two parameters, one being name, the other one being first name. And now the implementation make sure that the parameters are set to the internal attributes accordingly. So we have name set to this name, and we have first name set accordingly to this first name, so to the local attribute or to the instance attribute of class person. Alright, so here we go. Now I want to further add two more methods, two types of methods to this class in order to be able to fiddle with the data a little later on as well, not just at the moment of time of creating such a person object, instantiating such a person object. So I will add two getter and two setter methods to this class. So first I want to set the name property. So this is it. Same with first name. Let's go and copy this method. Okay. And now we need to getter methods as well. We can copy the two of them here, just give them different names. Get name, we don't need this anymore, but therefore we need a string return type, and we just return the name of this person. The same here, don't need this anymore, and we return first name accordingly. Alright, so the person class is ready to go. The next class I want to implement is SAP HR, so the base class or the foundational class of the SAP framework, which corresponds to SAP HR module. Again, I have created a respective skeleton class over here. Now let's have a look at the methods that we need there. There is a method which is called hire person, use person, fire person, and then forget person. And there is a fifth method which is called lifecycle manage person. I will start off with the abstract methods, the ones that are tagged abstract in the respective class diagram. Okay, so we have public void, public abstract void. Let's go with use first, person. Abstract void fire person. And public abstract void forget person. The hire method, as we can see in the respective algorithm to the right, seems to return a Boolean value, even though this is not clearly indicated here in the UML diagram. So I create a slightly different schema or a slightly different signature for that method, which is also abstract, but this time it is expected to return a Boolean value, the hire method. So, alright, here we go. Now the only method that obviously already provides an implementation on this level is lifecycle manage person. Let's go with this one now. Public void lifecycle manage person P. And the implementation is quite straightforward, and we can just more or less copy it over from the annotation here on the slide. It goes if hire P, then we use P, fire P, and forget about P at some point in time in the future. So this is already it. This is SAP's implementation of their core module. Now it is up to the companies implementing the SAP compile base and customizing it to their respective needs. So it's up to these companies now to actually implement and provide implementations for the respective stop methods, which means for hire, for use, for fire, and forget, in order to actually come up with a solution that meets their respective needs and requirements. Okay, the next class I want to implement is SAP HRA, so an actual implementation of the base class, SAP HR. I've already created the respective skeleton class over here, and the one bit that is still missing is the link, so the extends link, which makes this class inherit from SAP HR. And by introducing this inheritance link, the compiler expects us to provide implementations, so to create implementations for all the abstract methods that we have added to this class. So we need to now come up with an implementation for the 4 methods in order for the compiler to actually have us pass through the gates. I copy them quickly from there, get rid of the abstract keyword, and also it's up to us now to actually provide an implementation for them. Let's start with the use method. Get rid of that bracket down here. Okay, so let's start with this one. I just do some console outputs, so I just plot something out into the console window here. No real implementation, obviously. All right, whatever. Well, dear person, get this job done. Let's copy this quickly. We need to have implementations on for all these methods now. Fire, please leave this company. Dear, yet again the person is meant. Then we have another one. And this is to forget somebody. Who is person whatever. And the last one is really to provide an implementation now, to create an implementation for the higher step. So this is to actually realize a policy or a criterion that the hiring is based upon. Let's go with a simple one here. So return pay get name. This is a string, remember, starts with the following. Let's go with my name. So only people with the last name Arnold would be actually hired by this company. What a surprise. So, all right, I saved that one. Now we have a first implementation ready to go. So there is only one class missing now, even though it is not on the UML diagram anymore. This is the class that provides an entry point for the operating system and for the whole program to be actually executed. Also for this class, I've created a respective skeleton code fragment already. I call this class SAP HRA executable, and the first thing we need to add to the class is a main method as an entry point for the operating system and for the program to be executed. So the standard signature for this method is public static void. The name has to be main, and the only one parameter that we actually need here is of type string vector or string array arguments. Now the implementation. So we pick two persons or two people, person P1, and create on the heap the respective object of this type person. Let me check quickly again. The parameters were string, so name and then first name. So need to take this into account. So name is first. Let's create myself as one person and another person P2, and let's create this other person. Let's use Ravi. So last name Bindra, first name Ravi. Next step is that we refer on the level of the reference variable within this local method to the ultimate framework class to be as generic as possible for future extensions of this program when we introduce other implementations of SAP_HR. Let's call it HR system, this one. And now we create an appropriate object on the heap, which obviously has to point to an implementation of this abstract class. And for this one, we use the only implementation that we currently have, which is SAP HR_A. Now that we've created that class, that concrete object on the heap as well. Oh, there is then the new operator is missing. Now that we've created that one, we can actually call the respective method, which was lifecycle managed person. Let's copy it over. Lifecycle managed person, and we add P1, for example. Maybe let's do the following. Let's add an else branch to it. So if somebody was applying for a job but was actually not taken, we plot something out into the console window, which goes system out print ln. Sorry, but this job can't be offered to you. Dear, let's be polite, P, right? So we have added an else branch now. What's wrong here? Can't be resolved. Oh, obviously not. HR system. This is how we call this variable. All right, so we have it now. Let's try to call this twice, and let's give Ravi a try first, and then me in a second go. There is one more thing that we actually have to do. We have to flag this method as final, because otherwise the implementer of this class could easily override the method lifecycle managed person and actually fiddle with the algorithmic structure, and this is not what we want. And there is another step that I want to quickly do, which is overriding the objects, the object class's standard method, which is toString, to come up with a different implementation for this, because otherwise just hash tags will be plotted out which refer to the identity of an object, and this behavior I want to override. So public string toString, and we go with a person-specific implementation of the toString method. And this one goes return. Well, let's go with just first name and last name, or just name in this case. Okay, that's it. That's good. Now we've implemented the whole thing, pulled everything together, and are ready to actually execute the program. Okay, so, well, let's go and execute it quickly. We run it as a Java application, and we see the output down here. So the first one was generated by this call, where we had Ravi apply for the job, and where we realized that this was actually plotted out to the console window just with Ravi's details attached to it. The reason for that is that the implementation that we actually referred to and pointed at here as the object that we created implemented the hire method such that only a person with the last name, so the name attribute being set to Arnold, would be hired by that respective company. This is why Ravi did not get that job, and this line was plotted out to the console window. Now, second attempt that was made was me. I was a little more luckier, if this can be said like that over here. So I was actually welcome. I was first hired, obviously, then I was welcome. We look back to the backbone method, so this whole method was actually executed. First I was hired, then I was used, fired, and then forgotten. But I was done so along the implementation of this implementation class, or the actual implementation at the company A. So while SAP was providing the algorithmic structure on the level of the template method, which in this case was called lifecycle manage, so while this was kind of fixed and finalized on the level of the foundational framework of SAP, the actual implementation that we did was providing and extending the actual implementation of the respective functional steps that the method, the algorithmic structure, was altogether based upon. So the function endpoints, so to speak, were implemented by company A and within this class, whereas the algorithmic structure was implemented once and forever by the SAP company and was set to be final here. So nobody would be able anymore in future to actually override it. The whole thing led to the behavior that we can see down here. So I was first hired, as mentioned already, then I was welcome at that company. You see my name was squeezed into the the respective welcome statement, very much along this line here. So P was just kind of, that was the parameter that was given to the method, and this is me, or this was me. And then later on I was asked to leave the company, and a little later was not remembered anymore by the company itself. So I hope that you have seen that between the template method pattern, so the description, the generic description that we can see over here yet again, the application of the template method pattern, which we saw over here, so the application to the SAP problem as we had it at hand, and then finally the implementation that we based upon all of that here in Eclipse, so in the Java language in this specific case, that there is a clear trace between the three steps, and that finally the design that this code artifacts here, that the solution was built upon altogether, directly traces back to template method, to the template method design pattern, so that everything that we harvest over here from a design, good design practices perspective, is actually going back to template method. So we reused the conceptual nugget, the conceptual insight of the template method pattern. We knew before we actually applied it what we buy into, and then we just kind of walked our talk to the end and harvest results over here as just expressed in Java terms. I hope you enjoyed this session and that I was able to stipulate your curiosity. Again, this was a very high-level introduction into the concept of patterns as well as pattern language, and also a very quick glance at an application of the template method software design pattern. While this example was consciously used on a software design level, the patterns that Novartis has already created, as well as those that we are approaching right now, provide architectural guidance, which clearly goes beyond code artifacts. Just make sure you don't get this wrong. If you are keen now to understand how patterns are used within Novartis IT, in order to significantly boost our efficiency, our level of more meaningful standardization, as well as how patterns from a common language form a common language to better understand and exchange views and opinions all among us, then watch out for more videos to come soon. Also, and if you have any further questions, ping me anytime at ingo.arnold@novartis.com.